For this problem, we have a 6.5 microcoulomb charge, which I'll call Q1 at the origin. And we have a negative 3.3 microcoulomb charge over here that I will call Q2. These are initially separated by an initial distance of 0.26 meters. This thing has a mass of 35 grams, so 0.035 kilograms. And it starts at rest. V0 is equal to 0. And it moves 11 centimeters. Now, which direction is it going to move? Well, opposite the tract. The electric field, due to this positive charge, points, radially outward in all directions. So this electron, or not electron, this negative charge is going to want to move in the direction opposite that field until it reaches a final distance here, RF, of 0.15 meters. Right? It's going to move 11 centimeters. Okay, so how can we need to figure out the final velocity v after it moves 11 centimeters. Okay, so you can't in this one use F equals ma. The sum of all forces is equal to mass times acceleration. The reason why you can't is the same reason you can't do this with pendulum problems or spring forces. The force is not constant, therefore the acceleration is not constant. Right? And you'd want to do V squared equals V0 squared plus 2a delta x. Nope, can't do it. Because those equations of motion, those are 5 equations of motion, assuming constant acceleration, which you do not have in this case. Right? Because the field, due to this charge Q1, that electric field, is non-uniform. And so the force that charge Q2 feels is non-uniform. So we have to use work energy. Right? The sum of the works done by all the forces is equal to the change in kinetic energy. And in this case, we're told that no other force is relevant to the problem except for the electric force. So I can write that the work done by the electric force is equal to delta K. So how do we find the work done by the electric force? Well, there are 3 ways to find work. The first way is F delta S cosine theta, and that doesn't work here because the force is not constant, right? This method only works when everything is uniform. The field is uniform and the force is uniform. Second method is to use minus the change of potential energy, which we can use. And in this case, we have a formula for the change of potential energy of a charge moving through a field. It's going to be minus the charge multiplied by the change in potential that the charge is moving through, right? Q2 is immersed in the field of charge Q1. It's immersed in the potential of charge Q1. And so we have Q2 multiplied by the change of potential due to charge 1. So we need to find those potentials. We need to find the final potential due to charge 1 and the initial potential. So we'll start here. The final potential due to charge 1 is KQ over R initial, RF. Right? It's the initial due to charge 1. So I've got KQ1 there. So let's see, this is KQ, and then the final R is 0.15. So that works out to be 390,000 volts. And then the initial potential, KQ1 over R initial, is 9 times 10 to the 9 times 6.5 microcoulombs over our initial R up here, which is 0.26. So that's 225,000 volts. Okay, so the work done then by the electric force is minus Q1 or Q2 delta V1. So minus 3.3 times 10 to the minus 6. Now notice that I'm including a minus sign here, right? Unlike this equation where we put absolute value signs around everything, the potential energy expression, we don't use absolute value signs there. We've got to take into consideration all of the positive and negative signs. Q2 is negative, we got to include that in there. And so this negative and that negative is going to cancel out. So then VF minus VI is 390,000 minus 225. So that calculates out to be 0.5445 joules. Now it's positive. That's not surprising, right? It shouldn't be, because the electric force, right? The electric force on charge Q2 is in that direction, right? Because the electric field points in that direction, but the negative charge wants to go against the field line, and so the electric force is in the same direction as the displacement vector, delta S, and since the force is in the direction of motion, the work done by the electric force should be positive. So I'm glad that that is positive. All right, so now I'm going to go from here. I'm going to plug that in down here. We have the work done by the electric force, which is 0.5445. That's equal to 1/2 mv squared minus 1/2 mv naught squared. But then that term is 0, of course, because v naught is equal to 0. Remember up here we said that this particle initially begins at rest. And then I plug in a mass of 0.035 kilograms here, and I solve for v, and I get 5.6 meters per second.